All right, welcome back. We're going to go ahead and continue our discussion. So we just talked about angular acceleration, and to go more into that, we want to talk about something called tangential acceleration and centripetal acceleration. So tangential acceleration is going to be the change in the change in the magnitude of velocity and not its direction. So its direction is going to stay the same, but the magnitude will change, okay? And then centripetal acceleration is a change in the direction of the velocity, but not a change in its magnitude, okay? So here is a pictorial representation of what I'm saying, okay? So if we're traveling along some curve, okay, my tangential acceleration is going to be in this direction, okay, and my centripetal acceleration is going to be toward the center of the rotation, or the circle, if we're traveling along a circle, okay. And we have the relations of how we get to one another, kind of what we looked at in the last slide, but in a little more depth. So we have that our tangential acceleration, okay, is going to be a sub t, and that's going to be equal to our change in velocity over a change in time, okay? So it's basic acceleration, that's our tangential acceleration. Now, if we take that further and go ahead and replace our velocity to equal our radius times our angular velocity, okay, we can rewrite it in such a way that we can relate our tangential and centripetal accelerations, okay. So our centripetal acceleration, as we saw from the last slide, is our change in omega, or a change in angular velocity over a change in time. And because we know that, we can go ahead and relate these two accelerations. Okay, so we have our centripetal and our tangential accelerations related here, such that our tangential acceleration is equal to our radius times our centripetal acceleration. Okay, so this is a sub c, or alpha. Okay, so let's go ahead and look at a few examples with this. Okay, so we'll start with this one. It's a little small. Let's go ahead and zoom in. Example 10.2, we're looking at the angular acceleration of a motorcycle wheel. Okay, so it says a powerful motorcycle can accelerate from 0 to 30 meters per second in 4.2 seconds. And it asks what is the angular acceleration of its 0.32 meter radius wheels. Okay, so again, we just saw, oh no, give me 1 second. We want to erase, but not that big. Okay, that looks better. Okay, so let's go ahead and get pencil out. Okay. Oh, I don't like that either. Sorry, I'm trying a new what is this called? Program. And I'm not loving the pencil choices and such. Anyway, okay, so let's go back to the example. Again, we have a motorcycle that can accelerate from 0 to 30 meters per second. So that's going to be our velocity. Velocity, come on. Velocity, oh boy. Hold the moment. Why is it so large? Okay. So, I'm sorry. our velocity is 30 meters per second, okay? And our time that went by is 4.20 seconds, okay? Our radius of the wheel is 0.32 meters. So we want to know what its angular acceleration is. So we can find our tangential acceleration, right? That was just our delta V over delta T, okay? But it is also equal to R times alpha. Okay, so we saw that just in our PowerPoint. We can double check that that is right, and yes, it is. Okay, so let's go ahead and use this knowledge to determine what this value is. Okay, so we can say that rewriting this will give us alpha equals delta V over delta T, okay, divided by R. Okay, so alpha will be our 30 meters per second divided by our time, which was 4.20 seconds, and divided by our radius. So we should get, let's see, 30 divided by 4.2 divided by 0.32. And I get 22.3. And you can notice here that our meters will cross out. See how our meters and meters cross out? So we're left with almost like it doesn't have any units. But since we are looking at a circle, again, we will call that radians, okay? Because it's not rotations, it's the number of radians, okay, per seconds squared. Okay, so when we look at our alpha, when we look at angular acceleration, remember that our units are always going to be radians per second squared. Okay, just try to remember that. You kind of have to just insert our radians. So just keep an eye on that. Keep remembering that. Okay? All right, so we found our alpha. Okay? And so we can go ahead and move on to another example. Okay, so this one we are going to calculate the acceleration of a fishing reel. Okay, so that's what we're looking for. So the problem states we have a deep sea fisherman who hooks a big fish that swims away from the boat, pulling the fishing line from his fishing reel. The whole system is initially at rest, and the fishing line unwinds from the reel at a radius, I'm going to go ahead and write this out, of 4.5 centimeters or 0.045 meters, okay, from its axis of rotation. The reel is given an angular acceleration of 110 radians per second squared for 2 seconds. Okay, as seen in this figure. So we want to first determine the final angular velocity of the reel. Okay, so let's see. We know that alpha is equal to delta omega over t, right? And our delta omega is going to be equal to a final value minus an initial value, right? Okay, but we know that initially this entire system was at rest. Okay, so this term will actually go to 0. Okay. Oh, that shouldn't be in meters per second. That should be radians per second. Okay, so we can go ahead and use this and solve for our final velocity. Again, it's It's our angular velocity, okay? So that is going to be alpha times our t. So that'll be 110 radians per second squared times our 2 seconds. So that's going to be 220 radians per second. Okay. So that is going to be our angular velocity of the reel. Now we want to know at what speed is fishing line leaving the reel after 2 seconds elapses. So now we want to know the speed. Whoops. Oh, shoot. Okay. The speed after leaving the reel. Oops. So we want to find some velocity here. Okay. So let's go back to our equations and try to figure out what we can use. So we want to find our velocity, right? But we do know our time. Okay, so let's see. So let's look at these equations here. So our velocity is related to our tangential velocity, okay? And that's also related to our alpha. So I would say we can do something similar to what we did in this previous problem, okay? And determine from there our velocity. So that's what I'll do, is I'll use something similar to this. So we're gonna have V, or delta V, over delta T equals R times, I think it's alpha. Okay, so this is given to us, this is given to us, and this is given to us, and this is what we want to know. Okay, so we have our V equals R times T times alpha. So our radius was 0.0, let's see, 45 meters. Our time is 2 seconds. And our alpha was given to us as 110 radians per second squared. Okay, so let's go ahead and calculate that. And we get that our velocity is 9.9. And let's see, we have meters per second. Okay. So this is my velocity of the fishing line leaving the reel. All right, so let's go ahead and pause here on this problem, and then I will come back to it in the next video. I think we need a little bit more information as far as the kinematics of rotational motion goes. So here we have these relationships between rotational and translational motion. And so we have our motion in, let's see, it's kind of, we're relating these two things, okay? So remember that our omega was equal to our delta theta over delta t. So we're just relating these now to these different concepts, okay? So these are the rotational kinematic equations, and these are in your textbook. You can, pause this video if you want and kind of take a screenshot or something. If you want, you don't need to, it's in your book. So then we will use these equations to solve the rest of that problem, okay? So I will see you back in the next video to do that.